Okay, today we are going to start with the first conversion unit in a refinery. So far, what you studied was basically what is chemistry of crude oil, how do you characterize this very complex mixture, what are the various ways by which we understand what is this crude oil. And then after that, we actually got around to make, define some definitions like API, Watson K, ASTM D86, D1160, D2887, etc., etc. And then actually the intercorrelations between these various properties. And then from there, we actually came to the discussion on the crude unit, where based on distillation or more precisely relative volatility, we were able to separate out the various fractions of the crude oil, all the way from fuel gas to LPG to light naphtha, heavy naphtha, kerosene, and vacuum. These some of these products that useful. Okay, the straighter naphtha that comes out of the crude unit, you cannot put it in your car and expect the car to run. And you already know that I had mentioned earlier that this material has too much of normal paraffins. And so normal paraffins is not very high octane material. We need minimum 92 octane to run our vehicles. So catalytic reforming is one of those technologies which actually help you to run your car. And as I said earlier, before I finished last Friday, that both the motor vehicle development to what it is today, in terms of the ruggedness and the robustness of an IC engine that you see today, as well as the development of catalytic reforming, has actually happened hand to hand, like made for each other. If we wouldn't have gasoline-driven vehicles today, this technology would not have developed, and vice versa. If this technology would not have developed, you and I would not be actually riding on gasoline-driven vehicles today. Okay, so this technology is extremely important, and we will actually cover this very important technology in two parts. In part one, we will actually study, the modern gasoline specifications, the material that you actually put in your two-wheeler or in your car when you show up at a petrol station, and also the renewed interest in oil to chemicals. So basically, in terms of aromatics like benzene, toluene, and xylenes. We'll go through history of catalytic reforming. It's a very interesting history, actually, of catalytic reforming, how the whole thing started, and then how it picked up, and then thermodynamics and kinetics of catalytic reforming. And then, of course, once we discuss the kinetics of catalytic reforming, we'll discuss, the reactions that happen in catalytic reforming, both desirable and undesirable, and also the catalyst. And then in second part, after we finish part one, we will talk about the various technologies which are out there in the refining industry, more than 600 refineries. Like crude and vacuum distillation unit, it's very rare not to find a catalytic reforming unit in a refinery. Okay, even Digboy refinery, which is as small as 0.6 million ton, 0.6 million ton, which is only 12,000 barrels per day. The smallest refinery in the world. We have it in Digboy. We have a very strange dichotomy in our country. In our country, we have the smallest refinery in the world, which is 0.6 million ton per annum in Digboy, in the far east. And we have the largest refinery in the world in Jamnagar, in the far west. We have the oldest refinery in the world in the form of Digboy, which is 1901. So it's more than a century old. And we have a most modern refinery in the world, like the Jamnagar refinery. So we have these two strange, dichotomies in our country, and everything else falls in between. So as always, whenever I actually start something new, I'll always start with this particular slide in order to actually get your gears in place in terms of what is it that we are talking about. So if you recall, from the atmospheric distillation unit, we actually say take out the wild naphtha, right? And the wild naphtha, which contains both LPG as well as naphtha, that is actually distilled in a column called a naphtha stabilizer. And from the naphtha stabilizer, generally this naphtha is taken into another column where you distill out the light naphtha and the heavy naphtha. The heavy naphtha actually comes here. And this heavy naphtha is first hydrotreated, and I'll talk about that later, why we hydrotreat it. And then actually it is the major feed, the staple diet to a catalytic reformer. So the heavy naphtha, which is something like a fraction boiling between 105 to something like 165 or 180 degrees Celsius, is what is actually added as a feed. Why we need a hydrotreater? Actually, this naphtha contains impurities like nitrogen and sulfur. And the catalyst which we use in catalytic reformer is highly susceptible to sulfur. So we actually hydrotreat the naphtha to reduce the sulfur down to less than 1 ppm. I repeat, we hydrotreat the heavy naphtha to reduce the sulfur down to less than 1 ppm. And then by doing that, we actually, and also the nitrogen. So nitrogen we convert to ammonia and we separate it out. And sulfur we convert to H2S and we separate that out. And so basically the sweet naphtha, that is naphtha which doesn't contain any sulfur and nitrogen, goes into the catalytic reformer. And the catalytic reformer, the product is called reformate because it is coming from the reformer. And that actually ends up as one of the major components in the gasoline blending pool. When I say gasoline, please remember that this is a technical word used in the refinery for petrol. The petrol that you and I know, which we fill in a petrol station. Adding to that blending pool, which is actually all the streams which are blended to make the gasoline, finally, the final gasoline that is sold in the petrol stations. You have other streams like coming out of the isomerization unit. We'll actually discuss and cover this also later after we cover catalytic reform. And there's a major stream coming out of the FCC. It's called FCC gasoline and alkylates. And in fact, there's a stream coming from the hydrocarbon. In other words, any heavy naphtha stream, which is, or even, something like boiling above 95 degree. Any naphtha stream which can be actually blended into the gasoline pool is a candidate for blending into the gasoline. Okay, provided the gasoline overall actually meets the specifications that are laid down by the government on the gasoline which is sold in the petrol station. Same like the water bottle that you buy, there's a specification label on that given by ISI, which is Bureau of Indian Standards. Bureau of Indian Standards actually has an ISI mark. So even the gold that you buy, there's an ISI quality assurance. So similarly, on gasoline, diesel, LPG, any product that you buy, which is a consumer product, there is actually a specification laid out by BIS. And actually the oil marketing companies have to meet that specification. So the specification has to be met by this gasoline by actually optimum blending of these various streams to meet the final spec. And I'll talk about those properties. So the next portion, the next talk is basically on the gasoline fuel properties. There's a very interesting history worldwide. In fact, when catalytic reforming was not so popular, actually people used to add tetraethyl lead, TEL, in naphtha to be able to meet the octane requirements. And in those days, I'm talking about 60s, 70s, 80s, even 50s. The vehicles were not the kind of modern vehicles that you see today. This is, fuel injected system. They were carburetor-driven engines. And those carburetor-driven engines actually, and the speed requirement was not that high. vehicles did not travel long distances. So basically, the requirement in terms of fuel also was low. Number two, actually, there was no awareness that these vehicles pollute the atmosphere. A, because the number of vehicles were relatively much lower, and it was more like a property of rich people. So in even in our own country, when I was, in fact, when I was growing up, actually, in fact, in my lifetime, the first time I actually bought a car was in 1992. This was after I had actually, put almost like 16 years of work in EIL. And that too, I bought a second-hand car because I could not afford a new car. So actually, at that time, we had only Fiat and Ambassador. None of these new cars that you see made by Honda or Hyundai, even Maruti did not exist. Maruti Suzuki also did not exist. I'm talking about our own country. But even worldwide, where you had all these car manufacturers, we used to add tetraethyl lead in the gasoline. The world actually slowly woke up to the fact that tetraethyl lead is dangerous for human beings because it gets emitted uh, along with the combustion gases from the tailpipe of the car. And actually, there was a lot of medical studies done to confirm the ill effect of lead, including actually genetic deficiencies in unborn children, etc. And so the Western world, where the car population was relatively much higher as compared to India, there they actually started banning addition of lead in the gasoline. And but in our country, actually, I remember in 1994, that was the year when I left Engineers India Limited and joined Technip. The first specification came in terms of reducing the lead in the gasoline to be sold. And that was actually implemented in the 4 metros to begin with, that is Delhi, Bombay, Calcutta, and Chennai. And before that, of course, there was no such requirement. So basically, the oil companies were adding lead. In fact, you won't believe it, in January 1994, I had visited Barauni refinery. And in fact, one of the technologies I commercialized there was primarily to help the refiner to reduce the lead addition in the refinery. So 1995, this all actually in our own country happened because of the order passed by the Supreme Court. Uh, I mean, frankly and funnily, I belong to this industry, and I'm always sad to say that given to the oil marketing companies and to the oil companies, they will never take any initiative on their own. And they keep on convincing people that what they are doing is right and there is nothing wrong in terms of ill health, etc., etc. And that trend still continues. In fact, whenever we have some free time, we'll chat around that particular aspect, which is extremely important from a social perspective. But anyway, as usual, with the Supreme Court order and the deadlines and the timelines that the Supreme Court laid down, 1994 lead was reduced in the gasoline, and then actually the same thing happened within 2 years in the entire country. And then, of course, later on, in fact, what the Supreme Court did was actually they gave the target. Supreme Court laid down the target in terms of a roadmap of how actually the oil companies should keep on reducing the lead in the gasoline. So 1995, almost zero leaded gasoline was introduced in the metros. In fact, friends, you might find this funny, but actually, in those days, if you go into a petrol station, there were two petrol pumps. One actually had a heading saying leaded gasoline, and the other said unleaded gasoline. And there was a price differential between the two. Okay. The unleaded gasoline, of course, both had same octane. And then slowly and steadily, the unleaded octane was phased out. 1998, in fact, completely unleaded gasoline in all the state capitals. And since 2000, for the last 22 years now, we have unleaded gasoline in our country. But if you look at this time span, it took around 6 to 7 years for our country to go from a fully leaded gasoline to a completely unleaded gasoline. But on the other hand, if you look at the Western world, including Europe, US, and some of the other developed countries, they took almost close to 15 to 20 years to do that, to go from fully leaded to fully unleaded. And one single technology which actually helped to go from fully leaded to fully unleaded gasoline is catalytic reforming. And in fact, that's why actually the oil companies asked for some time, at least 2 to 3 years from the Supreme Court, because this particular unit had to be installed in most of the refineries in our country. So that is actually the importance of this technology. You and I, we breathe unleaded air primarily because of the invention of this technology. And coming to the gasoline specs, this is something very interesting. I mean, no discussion on catalytic reforming can happen until you talk about gasoline specifications. If you look at our own country, from the year 2000, when we went completely unleaded, to where we are today, and I'll talk about that, up to 2010, we actually graduated all the way from BIS 2000 to what is called as Bharat Stage 4 or Euro 4 equivalent. So we actually adopted the Euro 4 specifications and we called them as Bharat Stage 4. So the octane number slowly went up to 91, and in fact, now we are even talking about 95. The sulfur content, there was no spec. Can you imagine that? In fact, you'll hate the oil companies for this. I mean, there was no spec on sulfur in terms of gasoline. And then actually, when we made the unleaded gasoline, we actually put a 0.18% sulfur, which is like 1000 ppm. And then that was reduced to 500 ppm and then down to 150 ppm and then to 50 ppm. And today we have 10 ppm. You can see how the lead actually, why this small amount of lead is still put here, the number, is just to make sure that the old equipment that was used to store or transport gasoline, that might still have some leaded gasoline in it. So that might be leaching out, but of course this is more of an academic number. The other aspect is the benzene content. In fact, before 2000, there was no specification on benzene. And benzene is a carcinogen. See, why actually the specification of benzene suddenly became important? Because actually the moment you add reformate in the gasoline, and if suppose the feed to the reformer is the full range gas naphtha, that means IBP to 210, then the reformate will be rich in benzene, and we will see how that happens. And so suddenly the people woke up to the fact that by actually solving one problem, they have created another problem. That means by trying to reduce lead, they have actually introduced a carcinogen in the gasoline. And benzene, as you know, is a known carcinogen. So basically, then actually, again, there was an order from the Supreme Court to be able to reduce the benzene in the gasoline. So initially it was 5 ppm, 5 volume percent, then came down to 3 volume percent. And now actually it is less than 1 volume percent. And actually some of the refineries like in Reliance, we maintain below 0.6% benzene, because some of this benzene can actually come out of the tailpipe unburnt, as well as actually during handling. And when you come to the petrol station to fill your vehicle, you see the vapors coming out of your car, from your storage tank of your car. Those vapors are very, very rich in benzene. So then actually the other thing is the aromatics content. Initially there was no specification on aromatics. Then there were several studies done. In fact, one very important study was done by my institute also, at the Indian Institute of Petroleum, where we discovered that the higher aromatics like toluenes, xylenes, C9, C10 aromatics, which are very good in octane, but they can get dealkylated in the engine of the car, and they can get dealkylate to benzene, and therefore your benzene content in the tailpipe can go up. So now there is a spec of maximum 35% aromatics content, and olefin content also going down to 21%, and then now down to 18%. And the oxygenates in terms of either TAME or MTBE, or in terms of alcohol, what is being blended today. So as of today, we are on Euro 6, which I don't have a table for Euro 6, but Euro 6 is exactly same as Euro 4 or BS4, only that the sulfur content instead of 50 ppm is 10 ppm. Other specifications are roughly the same. So going from the BI specification, and so telling you the importance of this technology. What is reforming? Actually, as the word means, it is actually just modifying or restructuring the molecule. In other words, if the carbon range of the feed is, let's say, from C7 to C13 or C12, the product from this unit is also C7 to C12. So there is no change in the carbon number. In other words, there is no polymerization that happens. There is no cracking that happens. It is just actually changing one kind of hydrocarbon type to the other type. And typically what we do is that we actually convert paraffins and naphthenes, whether these are paraffins, not mostly normal paraffins, and naphthenes like cyclopentanes and cyclohexanes, to aromatics, because aromatics have high octane. So this process converts paraffins to aromatics as well as to isoparaffins, and naphthenes primarily to aromatics. So there is no change in carbon number, okay, unlike other process units like catalytic cracking or hydrocracking, etc. What is the main purpose of the catalytic reformer? As I told you again earlier, see, there is another unit in the refinery called the isomerization unit. And this isomerate has some great properties, but also its RVP is high. So actually the reformate, it actually helps to complement the isomerate because it actually lowers the RVP. To compensate the presence, because the isomers generally boil at a lower temperature, so their vapor pressure is high. And the combination with isomerate also produces low benzene gasoline. So actually, generally the reformate has a higher benzene content and the isomerate has zero benzene. So they actually kind of complement each other. Also, the other major stream going into the gasoline pool, which is coming from the fluidized catalytic cracking unit. So that also is actually to limit the olefins and sulfur. So basically, so this FCC gasoline has good quantity of sulfur, as well as it is very, very rich in olefins. And so since these two streams have zero olefins and zero sulfur, they actually dilute the FCC gasoline. So of course, we know that as we go, as the vehicles are becoming more and more modern, it actually improves it is actually demanding a higher octane gasoline. This particular technology not only produces gasoline, but it can be used to produce some very high value products as well. And these are actually the building blocks for major petrochemicals, like for example, benzene, toluene, xylenes. Can I tell you that almost 70% of the aromatics that are produced in the world are actually produced from this unit. Okay, the rest of it is produced from the naphtha cracker I mean what we call as a steam cracker. Since actually you convert cyclohexane to benzene, so basically naphthenes to aromatics, you are actually reducing the hydrogen content of the hydrocarbon. So naphthene, which is C6H12, gets converted to C6H6. So you get 3 moles of hydrogen. So it's a significant hydrogen source. In fact, it is so significant hydrogen source that in our own country, not not too while ago, catalytic reforming used to provide hydrogen good enough for actually to do all the hydrotreating requirements that you have. So at that time, only Kero was being hydrotreated because there was absolutely no specification on diesel. And so actually the only kerosene which had, if required, is supposed to reduce the sulfur as well as to reduce the aromatics, Kero hydrotreating was being done. Now for that, actually the hydrogen source was catalytic reforming. So I still remember at Haldia refinery, there was no hydrogen plant. The Kero hydrotreater was being run by the hydrogen from the catalytic reformer. So for many, many years, catalytic reformer was the major source of hydrogen in a refinery. And it continues to be same. It continues to be so. I mean, people value the hydrogen as a byproduct from this unit. And also actually because of some cracking that happens in catalytic reforming at those temperatures, we get LPG. So LPG is also a byproduct from this unit. So this reformer produces not only gasoline, but alternatively, you can extract aromatics from this gasoline and produce aromatics. Like in Reliance, we actually don't use catalytic reformer primarily to produce gasoline. Some actually byproduct is there, which is goes into the gasoline pool, which we call as a light reformate. But the major aim of running the reformer is to make paraxylene. And as you know, Reliance is the third largest producer of paraxylene in the world. And this paraxylene is all produced in Jamnagar. In the two catalytic reformers, which are very huge. In fact, each one of them is about 6 million ton per annum catalytic reformer. So you can understand the importance of this technology. And as I mean, I very strongly believe that this is one technology that will live right across the time till the human beings are there on planet Earth. Because either we will need gasoline, or if we actually go completely to electric mobility and we don't need any gasoline any further, then actually this unit can start producing petrochemicals. And petrochemicals we will need anyway for our day-to-day living. What is the why we do? What is the what does it do? You know, catalytic reformer. It actually converts paraffins to isoparaffins and naphthens to aromatics. And the reason is that normal paraffins have a very low octane number. It has least desirable knocking characteristics, as we already studied in the first lecture. The isoparaffins are useful because they actually have a high octane, both isoparaffins and naphthens. But then in the reformer, the naphthene gets converted to aromatics. And the olefins, if they are present, also have high octane number, but actually, typically reformers, they actually process straight run naphtha. And as I've already told you, straight run, any straight run product. I mean, what I mean by straight run is the products which actually you obtain by distillation of crude oil. So the products that you obtain from the atmospheric distillation unit or the vacuum distillation unit, these are actually called as straight run products. And by definition, they don't have any olefins, but olefins have a high octane number. So the SCC gasoline, which has typically in the range of 33 to 35% olefins, so the FCC gasoline has a high octane. And amongst all of them, aromatics have the highest octane, as I think last time I shared you this table as well. So normal heptane is bad news. If you want to make gasoline, it is 0 octane. And almost some of these isomers as well. But as you go beyond, so if you take toluene, it is 120, dimethyl 2-pentene. This is like a pretty branched isopara. This is actually an olefin. This is a branched paraffin, isoparaffin, etc., etc. So basically, the purpose of the reformer is to try to maximize the aromatics and to be able to convert the paraffins to isoparaffins. Let me actually explain this kind of molecular transformation that happens in the reformer by this example. So let's say we have two feeds. Okay, one feed is given at the top and the other feed is given at the bottom. Now, if you look at the composition of this feed, typically this also helps you to understand that the typical feed to the reformer is actually somewhere between C6 to C10. All right, maybe C11, but nothing beyond C11. Okay, because I think from C9, C10, your kerosene range starts. So this particular feed has around 63% paraffins, around 23% naphthalene, around 13% aromatics, very little benzene, but toluene, xylene, and C9 aromatics. The feed below is got less paraffins and more naphthenes, roughly the same aromatics. Now the question is, which of these two feeds is a better feedstock for catalytic reformer? In other words, if I, as a refiner, if I'm given a choice between these two feedstocks, which one will I prefer? Actually, the one that I would prefer would be the one which has more naphthenes, because a cyclic naphthene, a cyclic paraffin, like for example cyclohexane, is very easy to convert to benzene. In fact, this is the first reaction that happens in a catalytic reform. The dehydrogenation of cyclohexane, cyclohexane or cyclopentane to corresponding aromatics. So if it is cyclohexane, it gets converted to benzene. If it is methyl cyclohexane, it gets converted to toluene, and so on and so forth. But paraffin is more difficult, and will understand it why. So actually, the top feed is called a paraffinic feedstock. The bottom is called more as a naphthenic feedstock. So you can see that this is the paraffinic, which is typically coming from a light Arabian crude, and a naphthenic, which is coming from the Nigerian crude. So this also depends upon the crude source. And now I think you would understand what I'm going to say. And that is that if I have got a huge catalytic reformer, like the one I have in Jamnagar, 6 million ton and into two. So there are two reformers, each of 6 million ton per annum. And I'm trying to maximize paraxylene production, okay, in Jamnagar. So what will I do? I will try to take a feed which is more naphthenic. And for that, I will try to choose the crude oil or buy that kind of crude oil which will help me to make more paraxylene. So you can see that there is a certain parameter called N plus 2A, which is a percentage of naphthalene plus twice the percentage of aromatics. And this is a parameter by which you define the goodness of the feed for making a reformate. Like this is 44.6, while this is 79.55. So you can see that this particular feed is N plus 2A is much higher. So anything higher than 70 N plus 2A is actually a good feed for the reformer, because it will actually maximize. It will produce more aromatics, or if you're making gasoline, it will produce a much higher octane gasoline. Okay, so this is what it is. If you look at the products, now, I would actually, request your attention to understand this. This is a very, very important slide. This is the typical reformate composition. So you saw the feed composition. This is a typical straight run naphtha, either coming from light Arabian or it is coming from Nigerian crude. But it has paraffins. It has actually, I've not shown isoparaffins, but there's both paraffins, isoparaffin, naphthenes, aromatics, no olefins. Okay. But if you look at the product coming out of the reformer, you'll see that there is hardly any naphthenes. Okay, all the naphthenes got converted, and there's significant quantity of aromatics. So something like going all the way from 13 to 10% aromatics, it goes to 69. So whatever naphthenes were present in the feed, 63%, that gets converted to aromatics. So 63 plus 10 is 73. 23 plus 13 is a plus, actually some amount of paraffins also get converted to aromatics. So generally around 70 to 73% is the typical aromatic content in the reformate. And you can see one more thing, that the isoparaffin concentration is much higher than that of the normal paraffin, because there's an isomerization activity which is created, which is actually supported by the catalyst that we use in catalytic reforming, which helps you to actually convert normal paraffins to isoparaffins. And and of course, small amount of olefins are also made, and I will explain to you why. So if you look at, suppose somebody gives you data, uh, in terms of paraffins, isoparaffins, olefins, naphthens, data. How do you figure out whether this is actually coming out of the catalytic reform? I have done that. If suppose somebody says, look, I want to set up some plant and this is the feed I have, which is naphtha. So when I look at that from three major things. One is the aromatic content, the second is the naphthenic content, and the third is the isoparaffinic content. So from these three, you can actually figure out whether this particular stream is coming from a reformer. So isoparaffin to paraffin ratio is almost like 3. Okay. And olefin, forget about olefin. Olefin is produced, but it's not that significant. But there's a big difference between the naphthenes and the aromatics. If you compare that with here, here it was roughly equal, and then here it is, we still have significant quantity of naphthenes, but there is no naphthene here. So any particular naphtha composition which has very close to zero naphthenes, you can be rest assured that it is coming from a reformer. Okay, so this is a signature, so as to say, of a catalytic reforming unit. Now, going to the history of catalytic reforming, actually, it's a very interesting history. In fact, the first, I think one of the earlier predecessors of the modern day catalytic reforming technology is actually, was called hydroforming. And don't get me wrong, this was very, very popular. In fact, more than 50 units like this were built during World War II, basically to provide, not only but also actually toluene for making it trinitrotoluene, which was used as an explosive. So first catalytic reforming unit went on stream in November 1940 in a refinery in Texas. And this particular technology was called hydroforming. It was actually two reactors. Two reactors were in operation, while two reactors were in regeneration. In other words, the carbon which gets deposited on the catalyst was actually burnt off. So the whole operation was cyclic. So it was a fixed bed unit operated in a cyclic mode. So it was the two reactors, let's say, but there were two parallel reactors in the operation mode. That means creating the reformate. And then once the catalyst gets deactivated, then you actually take it off and burn off the carbon, while then you use the other two reactors to continue the operation. And the catalyst which was developed and very successfully commercialized was actually 9% molybdenum oxide on alumina. So it went on for a long time. In fact, this was a major technology which actually provided gasoline, not only to vehicles, but also in those days, some of the planes also, like the fighter jets, used to run on gasoline. So hydroforming process made a significant contribution, or I would say significant discontribution. And because if this technology would not have been there, I mean, most probably the Second World War would not have happened. By producing toluene and aviation gasoline, but that went on for almost like 8 or 9 years, and then around the same time, a gentleman called Vladimir Hensel. He came up with what is called as platforming. It's actually the one of the earliest technologies of the modern catalytic reformer. This particular technology quickly replaced hydroforming. And so it was actually developed by Vladimir Hensel, who was actually a research scientist at a company called Universal Oil Products, which is called UOP. And in our industry, UOP is more like a name next to God, because almost every refinery in the world, and we have more than 600 refineries in the world, there's not a single refinery in the world which may not be using a technology developed and commercialized by UOP. And so this has been, so UOP can be actually, and everybody acknowledges that. Even the competitors of UOP acknowledge that UOP actually developed this technology. And that was done by Vladimir Hensel. In fact, just to make the things a bit lighter, in fact, I had visited UOP headquarters in Chicago. It's in the outer suburb of Chicago called Des Plaines, which is very close to the Chicago International Airport. And they have still conserved the table of Vladimir Hensel and all the awards that he got. They have actually put all the patents also, print out of all the patents they put on the wall, and also his laboratory where he developed this technology. So all of that is actually kept, for people to see, like a museum. They are not disturbed. The lab and his office and his workplace where he used to work. So that is the kind of importance. One single person in the history of mankind made such a big difference in terms of the way we move and in terms of our mobility. And it took UOP almost 8 to 9 years to commercialize this technology. So in 1949, the first unit based on this technology was commercialized. And this is why actually it replaced hydroforming. If you remember, hydroforming was based on 9% molybdenum oxide. Vladimir, he actually discovered platinum as a catalyst for this particular conversion. And he found that platinum is much more better metal as compared to molybdenum oxide in terms of converting naphthenes to aromatics and also to convert paraffins to naphthenes to aromatics. And that still continues. Today, in our reformer, we would have something like 300 tons of this catalyst. And 300 tons of this catalyst has 0.3% platinum. So you can do the maths to see how many tons of platinum we would be having sitting in that reformer. Okay, and looking at the price of platinum, you can calculate the total value of that material inside the reformer. So after that brief history, let me actually walk you through the chemistry and the catalysis, and we may not be able to cover everything today, so we will continue with that on Friday. We'll talk about the thermodynamics, kinetics, and the catalyst considerations, the chemical reactions, and finally, what is the catalyst that we use here. Just a brief recap of the thermodynamics that you might have actually studied in your undergraduate classes. If you remember, thermodynamics thermodynamics provides a broad guideline in terms of for us to trying to understand the possibility of occurrence of a chemical reaction. In other words, whether this chemical reaction will ever take place. On paper it may look good. For example, you might like to put methane plus something equal to something, but whether that reaction will ever occur. Okay, and the way to do that is to calculate the free energy change. So you take the free energy of the products and subtract the sum. So you do the sum total of the free energy of the products and subtract that from the sum total of free energy of the reactants, and you get what you want. So actually it also tells you the theoretical amount of products that will be produced. So if it is an equilibrium controlled reaction, so as you know, there are two types of reactions that are present in any type of chemical reaction that you and I know are basically two types of reactions. One, where actually the reaction is spontaneous and it goes all the way to completion, and it is limited by the amount of reactant that you have. So basically, the limiting reactant actually limits or decides like how much is the conversion. Like for example, let's say you take hydrogen, okay, and you burn hydrogen. It's a spontaneous reaction. Okay, hydrogen burns along with oxygen going to steam. Similarly, when you turn the knob in your kitchen for burning LPG, so The LPG, when it burns, like propane or butane, it actually produces carbon dioxide and water. And that's a spontaneous reaction. Okay, but it is limited by the amount of LPG that you put in through the burner. And but on the other hand, there are reactions which are equilibrium controlled. Like for example, the way we make ammonia. So nitrogen and hydrogen reacting by the Haber-Bosch process to make ammonia. Now that's an equilibrium control reaction. In other words, given the opportunity, ammonia will also convert back to nitrogen and hydrogen. So these are like incomplete reactions, and the final equilibrium depends upon the thermodynamics. So what thermodynamics tells you in an equilibrium control reaction is that at equilibrium, at a given temperature and pressure, what will be the composition of the products and how much reactants will still be available. So on the other hand, so thermodynamics, but doesn't say nothing about when the reaction will happen, how much time it will take, and whether it will take 30 seconds, whether it will take 1 hour, whether it will take 2 hours, or whether it will take 10 years, we don't know. But it does tell you whether the reaction will occur or not. Like for example, this is a good example for you to understand what I mean. That a reaction may have a very large negative delta G. That means it is feasible reaction. If there's a large negative delta G, that means change in free energy. But the rate may be so slow that there is no evidence of it occurring. For example, graphite converting to diamond form of carbon. So carbon in the graphite form converting to diamond actually. The free energy change is quite negative. But the rate of reaction, as we know, in Mother Earth is so slow, it takes a huge amount of time to actually convert graphite to diamond. And so actually thermodynamics doesn't tell you that when actually this reaction will happen and how fast the reaction can be. So that is where actually the role of catalyst happens, as you know. It's a material, catalyst can be of both types. It could be either a heterogeneous catalyst or it could be a homogeneous catalyst. But the primary role of the catalyst to increase the rate of the reaction at which the chemical system approaches equilibrium. So we know that equilibrium will get achieved at that temperature and pressure. Catalyst cannot do nothing about the equilibrium. It cannot disturb the equilibrium because that is decided by thermodynamics. But actually, catalyst will help you to get from the reactant to the equilibrium composition quickly. So it affects only the rate of reaction. It changes neither the thermodynamics or the equilibrium composition. And we already know this Arrhenius equation. Let's say, for example, this is the total energy content of the reactants A plus B going to a product called based on these reactants. And you have actually a kind of energy of activation, which it has to go around. So if you look at the total energy of the reactants and the net energy of the products, you can see that the delta E is negative. So the reaction will happen to go from the reactant to the product. But it doesn't happen spontaneously. It has to go through an energy activation. And this is actually what the catalyst does. It actually reduces, it reduces the energy of activation. So the activation energy is the energy required to overcome the reaction barrier, and it determines how fast the reaction occurs. So basically, what the catalyst does is actually it provides an alternative path. This cartoon actually gives you a good idea of what the catalyst does. Is actually we need to go from here to the other end of the mountain. So one way is to climb the mountain, which is very slow. On the other hand, you could use a catalyst to actually help you to get to the other end much faster. So it actually reduces the activation energy for both forward and backward reaction. Now, coming with that background of thermodynamics, so I actually try to recap this background that you already have of thermodynamics and reaction is because we are going to discuss both of them in very great detail in terms of its application to catalytic reforming. And this particular slide is extremely important because it actually tells you what Vladimir thought. So in UOP, when Vladimir started to develop this catalyst, he looked at two things. One is that he was looking around for a metal which can actually promote or reduce the energy of activation for dehydrogenating either a paraffin or naphthalene to aromatics. And although molybdenum was being used, he tried to look for other metals and tested out and tried out many metals. And he then found that platinum was the best. So the platinum, so basically the catalyst of the catalytic reforming catalyst does have platinum on it. And the other aspect which Vladimir thought is that if suppose I have to improve the octane, I need to convert the paraffins to isoparaffins as well. And if I have to convert the paraffins all the way to aromatics, again, actually, I have to change the molecular structure of the paraffins. First of all, to dehydrogenate to olefins, and then to rearrange the olefins to make naphthenes, and then from naphthenes, again dehydrogenation to aromatics. So actually, there was another functionality required, which actually helps and supports the isomerization function. So basically, the catalyst which is used in catalytic reforming took birth by actually an optimum combination of two functionalities. One is the dehydrogenation function, which is promoted by the metal, in this case platinum, and then the rearrangement function, which is actually to promote structural changes, for which you need some kind of a minimum amount of acidity in the catalyst. So that actually led to the use of alumina, very high quality alumina, but chlorinated alumina. That means alumina which is already chlorinated, like aluminum chloride, which actually helps you to carry out these functions. So, so the catalytic reforming catalyst is actually called as a bifunctional catalyst. And why I'm trying to introduce this particular subject slowly to you, because as we go through other technologies of catalytic reforming, you will quickly understand that a lot of these catalysts actually do provide at least two functions. Most of the commercial catalysts that you see, even for non-refining applications, like even in petrochemicals, you will find that at least two functions are required. One is a metal function, which is actually the site for doing either hydrogenation or dehydrogenation, and also actually a chlorinated alumina, which can help you or some kind of a support. So basically, this platinum is impregnated on alumina, and that's how you make this catalyst. This is chlorinated alumina, which actually helps and supports these functions. So here we will